Okay, here we're going to talk about the remainder. So here's a estimation theorem for these Taylor polynomials, or Taylor's series. If there is a positive constant m such that the absolute value of the n plus 1th derivative evaluated at some value t is less than or equal to m for all t between x and a, and that includes the endpoints, then the remainder term in Taylor's theorem satisfies this inequality. So the absolute value of the remainder term is going to be less than or equal to that number m times the absolute value of x minus a to the n plus 1 divided by n plus 1 factorial. And if this condition holds for every end, and the other conditions of the theorem are satisfied by the function, then the series will actually converge to will converge to f of x. So let's take a look at an example of this. That way you'll understand how all of these terms play a role. Okay, so show that the Taylor series for sine of x at x equals 0 converges for all x. Now, we've actually already seen an example of Taylor series, but for sine x, I showed you an example of this earlier, but basically you get it by finding derivatives. So f of x is sine x, f prime of x is cosine x, f double prime is minus sine x, the third derivative is minus cosine x, and so forth. And so basically, let me just go ahead and tell you that we know that sine x is actually equal to this series plus the remainder term. Now, the first thing I want to mention is that all the derivatives of this function either involve a sine x or a cosine x, and they all have absolute values that are less than or equal to 1. So in this remainder term, we know that we can replace this m with 1. So we can replace that m with 1 because all of the derivatives of sine x evaluated at some number we know are going to be less than or equal to 1. So we can just make m be the 1, and then we take the absolute value of x minus a, and here we're using 0, so we're using x equals 0 here, so x minus 0 would just be absolute value of x, and then it's got to be the n plus 1th. So since this is the nth term, then we need to add 1 to each of these. So we would get absolute value of x raised to the 2x plus 2 over 2x plus, raised to the 2k plus 2 divided by 2k plus 2 quantity factorial. Now, the limit of this remainder is actually going to go to 0 as k goes to infinity. Okay, so the series for sine x actually converges to sine x for all x. So in this case, since this goes to 0 as k goes to infinity, then we know that this series actually converges to sine x for all x. In other words, the infinite series converges to sine x. There's 3 practice problems here. It just says show that the Taylor series for cosine x at x equals 0 converges to cosine x for every value of x. So basically do the same thing I just did for cosine x. And then this just says find the Taylor series for cosine of 2x at x equals 0. So basically you just take your result that you get up here and then replace x with 2x everywhere in the series. And then this says find the Taylor series for x sine x at x equals 0. So all you have to do there is go back up to the previous page where we got the series for sine x, and then multiply every term in the series for sine x by x, and that would give you this. So you can do those. They're not too terribly difficult to do. The Taylor series for e to the x at x equals 0 converges to e to the x for all x, but we still need to know how many terms to use to approximate a given accuracy. Let's suppose I wanted to calculate e with an error of less than 10 to the negative 6. Well, remember that the series we had for this was the series we had for e to the x, and so if you evaluate that for e to the first power, which would be e, that's e to the first power, right? It's e. So evaluate that for x equal 1, you would get 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial and so forth. And then you would have 1 over n factorial, and then your remainder term evaluated at 1. Okay, now if you go back and study the remainder term I gave you earlier, you'll see that the remainder term evaluated at 1 would basically be e to the power c over n plus 1 quantity factorial, e to the c over n plus 1 quantity factorial, and then we can actually assume that e falls between 1 and 3 because we know what e is, right? We know approximately what e is, so we can say it falls between 1 and 3. So therefore, if e falls between 1 and 3, then we can say that 1 over n plus 1 factorial, that the remainder term falls between 1 over n plus 1 factorial and 3 over n plus 1 factorial. Okay? So, and that's because if c is a number between 0 and 1, then e to the c would be a number between 1 and 3. So maybe I cleared that up there for you. So the remainder has to fall between 1 over n plus 1 factorial and 3 over n plus 1 factorial. Okay, now if you check the 1 over 9 factorial, it's actually greater than 10 to the negative 6. While 3 over 10 factorial, actually this should be less than. I thought that was wrong. So 1 over 9 factorial is greater than 10 to the negative 6, but 3 over 10 factorial is less than or equal to 10 to the negative 6. So if we let n plus 1 be at least 10, then that means n would be 9. Okay? So then, if I calculate e by adding these terms up all the way out to where n equals 9, then that would give me an approximation of e to the first power within 10 to the negative 6, or within an accuracy of 10 to the negative 6. So that's the truncation error. And these error formulas or error theorems can be kind of confusing for you to follow. I'm just going to leave you with this Euler's identity. And basically Euler's identity gives you a way to represent imaginary or complex numbers using sine and cosine, and it actually comes from thinking of the series. So for instance, e to the I theta can be written as a series, and then you can write that series like this, because here we know that if you square I, you get negative 1, so that's a negative. And then if you cube I, you get negative I, so that would be a negative I. And then if you raise I to the 4th, you're going to get positive 1, and so forth. And if you have I to the 5th, you're going to get I. And so basically, if you simplified this, you would get this. And then if you break this up just the right way, you can actually break it up to where you take all of the real terms here. This is a real term, 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 and put them by themselves. And then if you take all the imaginary terms, like here, 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 and put them together, and then factor the I out, well, it turns out that this portion is actually the series associated with cosine of theta, and this portion here is the series associated with sine theta. So it can be shown that e to the I theta can be written as cosine theta plus I sine theta. So in other words, if you had let's say if you had e, see if I can write this, if you had e to the power over 4, say that's theta, times I, then you can actually write that as cosine power over 4. Just bear with me here for a second. Cosine power over 4 plus sine power over 4 times I. So cosine power over 4 plus I sine I times sine of power over 4 is a way to write e to the power over 4I in terms of cosine and sine. So that's basically Euler's identity. It just basically uses these power series to actually write an expression for e to the I theta, where I is an imaginary number, or the imaginary unit. Okay, so that's it on this section. So let me see what we've got next. So I've got one more section I have to cover here to do this justice, and this involves some applications of these series, along with I'll introduce a series called the Fourier series, and the Fourier series is something that engineers use quite a bit.